Hey everyone, and welcome. Today, we are diving into the epic story behind, well, pretty much everything around us, from the giant steel beams in our cities to the very air we breathe. This is the story of two huge families of elements, the metals and the non-metals. I mean, have you ever really stopped to think about it? It sounds kind of like magic, doesn't it? You start with something that looks like, just a piece of dirt, and you end up with something that can hold up an entire city. That incredible transformation is exactly what we're going to explore today. All right, so first things first, let's meet our main characters in this drama. On one side, you've got the metals. You can think of them as the generous givers, always looking to offload something. And on the other side, we have the non-metals. They're the eager takers, always looking to grab something to feel complete. And their entire relationship, their whole story, it all comes down to one tiny particle, the electron. This right here captures their entire identity. See, every element on the planet just wants a full outer shell of electrons. That's when they feel stable. Metals, well, they only have a few electrons in their outer shell, so it's way easier for them to just give them away. And when they lose those negative electrons, they become positively charged ions, which we call cations. Non-metals are the opposite. They're almost full, so they are desperate to grab an electron to finish the set, and that makes them negatively charged anions. This give and take, it's the engine that drives all of chemistry. So at first glance, the rules seem pretty simple, right? Metals, they're shiny, hard, solid, and they conduct electricity. Non-metals, they're dull, soft, and terrible conductors. But chemistry just loves to break its own rules, and you've got to pay attention to these exceptions. You've got iodine, a non-metal that's actually shiny, or diamond, which is just carbon, a non-metal, and it's the hardest substance we know of. Then there's graphite, also carbon, that can conduct electricity. These aren't just fun facts. This is where you really start to understand how complex these elements are. And the metals have their own lineup of rule breakers. We picture metals as these tough, hard things, but you can literally slice sodium and potassium with a butter knife. We think of them as solid, but of course there's mercury, a liquid just hanging out at room temperature. And while most metals have crazy high melting points, you could hold gallium or cesium in your hand and they would just melt into a puddle. These are the guys that totally challenge what we think a metal is supposed to be. Okay, so now we know who they are. Let's talk about how they act. Because when it comes to chemical reactions, not all metals are created equal. Not even close. There is a very clear hierarchy, a pecking order, a power ranking that decides who's boss. I want you to picture this as a ladder. The metals at the very top, like potassium, are the most aggressive, the most reactive. They can easily go up to any metal below them, kick it out of a compound, and take its place. It's called a displacement reaction. The guys way down at the bottom, like gold, they are super unreactive. They just want to be left alone. Which, by the way, is exactly why gold doesn't rust or tarnish. It just doesn't care. So how do we know this power ranking is for real? Well, we can test it. We can put these metals into different showdowns, forcing them to react with everyday things like oxygen, water, and acid. And these tests really reveal their true character. So, first up is the reaction with oxygen. The general rule is pretty simple. Metal plus oxygen gives you a metal oxide. And the most famous metal oxide of all? You guessed it, rust. These oxides are usually basic, which means they can neutralize acids. But it's not that they react with oxygen, it's how they react that tells us everything. I mean, just look at the difference here. The metals at the top of our ladder, sodium and potassium, react so violently with just the air around us that they'll literally burst into flames. That's why they have to be stored under kerosene. Then you've got aluminum, a little further down. It reacts, sure, but it forms this tough, protective skin of aluminum oxide that actually stops any more corrosion. Then there's iron, which just rusts slowly over time. And at the bottom, gold and silver? Totally unfazed. They couldn't care less about oxygen. All right, next up, the water challenge. And man, their personalities really come out here. Those top-tier metals are so reactive they'll have a violent, explosive reaction with plain old cold water. But as you go down the list, they get pickier. Magnesium says, nah, I need some hot water to get going. And then aluminum, zinc, and iron are even more demanding. They won't touch liquid water, you need to bring them steam. And the ones at the bottom? Completely unbothered. Water is no big deal to them. And finally, the acid test. This one seems super predictable. When you drop a metal that's more reactive than hydrogen into an acid, it just boots the hydrogen out, takes its place, and forms a salt. You get a bunch of hydrogen gas bubbles as proof. It's a textbook displacement reaction. Seems simple, right? Well, almost. And that brings us to this guy. Meet the exception, nitric acid. It's the rebel of the acid world. See, it's a really powerful oxidizing agent, which is just a fancy way of saying it's incredibly good at forcing oxygen onto other things. So the moment any hydrogen gas tries to form, nitric acid slaps an oxygen atom onto it and turns it into water. So instead of getting those telltale bubbles of hydrogen gas, you just make more water. It plays by its own rules. So, for our final act, we're going to see how these two families, the metals and the nonmetals, actually come together to form these incredibly powerful alliances. And then we'll uncover the secrets of metallurgy, the science of how we free pure metals from the earth, where they're locked away in these strong compounds.
It all starts with a simple transfer of property. Take sodium, our metal, and chlorine, our nonmetal. Sodium has one measly electron in its outer shell that it is just dying to get rid of. Chlorine is just one electron short of having a full shell. You can see where this is going, right? Sodium happily gives its electron away, becoming a positive ion. Chlorine greedily takes that electron, becoming a negative ion, and now you have a positive and a negative. Opposites attract, and that powerful force creates an incredibly strong connection, the ionic bond.
And listen, if you ever need to remember the properties of ionic compounds, just think about plain old table salt. Why is it a hard little crystal? Because those ionic bonds are super strong. Why does it have such a high melting point? Same reason. You have to pump in a ton of energy to break those powerful bonds. And why does it only conduct electricity when it's dissolved or melted? Well, in the solid crystal, the ions are locked in place. They have to be free and mobile to carry an electric current. It all makes perfect sense when you think about salt. So, ionic compounds are incredibly stable. That's great for them, but it's a huge challenge for us because most of the metals we want are found in nature locked up in these super stable compounds. The science of breaking them out of that prison is called metallurgy.
Okay, before we go any further, just a little bit of quick vocab. A mineral is basically any natural compound you find in the Earth's crust. An ore is a special kind of mineral that has enough metal in it to make it worth our time to mine it. And the gangue, that's just all the useless junk, the sand, soil, and rock that's mixed in with the valuable ore.
Now, before we can get to the pure metal, we usually have to convert the ore into a metal oxide first. It's just an easier form to work with. And there are two main ways to do this: roasting and calcination. The difference is actually really simple. Think of roasting like a giant barbecue with tons of air flowing through it. That's perfect for sulfide ores. Calcination is more like baking something in a closed oven without much air. That works great for carbonate ores. Two different cooking methods, but they both have the same goal: turn the ore into an oxide. So, when you boil it all down, the entire massive process of metal extraction is really just three main stages. Step 1 is concentration. You get rid of all the useless rock, the gangue. Step 2 is conversion. You use roasting or calcination to get that metal oxide. And finally, step 3 is reduction. You use something like carbon to steal the oxygen away from the metal, leaving you with the pure stuff. That's the whole shebang.
And that brings our whole story full circle, doesn't it? We pour all of this energy and science into freeing pure metals from their ores. But the moment we do, the universe, through things like rust and corrosion, immediately starts trying to turn them right back into those dusty, crumbly oxides. It makes you wonder, our entire modern world is built on this constant uphill battle against nature's tendency to break things down. A pretty fascinating thought to end on. Thanks for tuning in.